along the wave. A brilliant experiment that demonstrates that property is the photoelectric effect. And here's how it works. You take a piece of metal. Now, metal is an array of metal atoms, and each of those atoms holds on rather loosely to its outer electrons. That's why the metal conducts electricity. Those electrons are rather free to move about the surface. Now, if you shine light on that surface, what happens? Well, you can shine light of certain wavelengths. Here we'll bring in a rather long wavelength, a red photon. And when a red beam of light hits that, you'll find for many metals, nothing happens. And even if you make the light very bright, very intense, nothing happens. If you bring in a green beam of light, this now has higher energy photons, shorter wavelength, higher energy. What you find is that electrons are indeed ejected. It's as if photons are striking electrons and kicking them off the metal. You bring in a more intense green light, and you get more electrons. They don't go away faster. You just get more electrons with a brighter light, all with the same kinetic energy. You bring in blue light, now higher energy photons, even a shorter wavelength, and you find that electrons with even higher kinetic energy are ejected. And again, the same correlation with brightness. If you make the light brighter, you get more electrons per second released. So it's as if the electrons are caught in a well, and there's an energy barrier that holds the electrons next to the metal. You have to overcome that energy barrier to eject the electron and release it from the metal. We'll designate this threshold energy, or this well depth, with the symbol phi. So red light, the photons of red light don't have enough energy to even get out of the well. So it doesn't matter if there's more of them, if there's more intense light, more photons per second, still none of the electrons leave the well. Photons in the green region, so shorter wavelength, have enough energy to overcome this binding energy of the electron being held to the metal, and a little bit of kinetic energy. More energy still in blue photons ejects electrons with even more kinetic energy. So it's as if the photons of light are coming in and jostling electrons. Like I'm holding on to this tennis ball. Photons are coming in and jostling them. The higher energy the photon, the more jostling occurs, until you get to a photon that can actually, higher energy now, break the photon free of the metal. Can I have my tennis ball back? If you go to higher and higher energies, bigger and bigger photons, in this case blue light, you'll eject the electron with more kinetic energy. Now brightness doesn't matter. We said, well, brightness is just more photons per second. That's just pep, 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 pep. But not enough energy, one photon per electron, to eject any single electron. But big photons, high energy, blue light, say, comes in and slams that metal and really sends the electron flying. Oh. Sorry, guys. High energy is what we have. So we can actually plot it. We can plot the kinetic energy of the electron versus the frequency of the light that we shine on the metal. And we know up to a certain frequency, no electrons are ejected. And then you'll reach that threshold. You'll just overcome the binding energy holding the electron to the metal, and you'll start to eject the electrons. Then higher frequency light just gives you more kinetic energy in the electron. The energy of the photon, we know, is h nu. So we can write the kinetic energy that the electron has is the energy that the photon comes in at minus this binding energy. So all the excess energy of the photon goes into kinetic energy. So you can write both energies in terms of photons, and you can realize there's a minimum photon energy required to eject the electron from the metal. If you look at different metals have different threshold frequencies. For instance, you could have a metal that's described by a blue photon as the minimum photon that ejects an electron. And higher energy photons give electrons with more kinetic energy. So this problem, the photoelectric effect, helps us understand the particle nature of light. And it's actually Albert Einstein, a genius who looked at this problem. Scientists, before the photoelectric effect was understood and the particle nature of light was understood, were taking their metals, shining lights, and increasing the intensity, figuring I should knock off more electrons. But increasing the intensity, very bright light, didn't do anything. And when you could eject electron, increasing the intensity didn't increase the energy of the electrons. You just got more electrons coming off with the same energy. Well, it takes a genius often to look at a very troubling problem and see it in a whole new light. And that's what Einstein did. He said, well, that looks like the light's behaving like particles. It looks like little bits of light are coming in. So a bright light is just lots of bits. But they all have the same energy. So those lots of bits eject lots of electrons, each electron with the same energy. So the photoelectric effect and Albert Einstein have helped us understand the particle nature of light.